All right, well, good morning. And we shall look at randomization tests today. Happy Monday. So, on Friday, we kind of did a run through of statistical inference, and we talked about hypothesis tests and confidence intervals and sampling distributions. And today we're going to do another hypothesis test, but it's going to be a randomization test. Now, to kind of, first we're going to just do a traditional z-test, okay? Two-sample z-test, which we can use to compare proportions. And so this is a review, again, of statistical inference, stuff you've seen before from intro stats. And so, the setup for a comparison of proportions might look something like this. And we might say, and I just made up these numbers here, but I just said, is the proportion of international students different for stats majors and math majors, okay? And so suppose I took a random sample of 150 students in statistics and 160 students in math, okay? And for the statistics students, 75 of them are international students. For those majoring in math, 64 are international students. And the question is, does the data I have provide evidence that the proportion of international students is different between these two majors? Okay, so we want to compare two sample proportions. My sample proportions for statistics is 75 divided by 150. I get a proportion of 0.5. For math, 64 divided by 160, I get a proportion of 0.4. And so the observed difference between proportions is 0.5 minus 0.4, 0.1. 10 percentage point difference between my two sample proportions. And so we are going to do a z-proportion test. So we set up our hypotheses. The null hypothesis, okay, so symbolically, we're going to just be p-stats is going to be the proportion of international students in the population for statistics, and then p-math will be the proportion of international students in the population for math major. Okay. Our null hypothesis is that the two populations have the same proportion, that p-stats minus p-math is the same for both groups, so the difference between them is 0. That's the null hypothesis. The alternative is that there is a difference, not necessarily positive or negative, and we're going to say p-stats minus p-math isn't equal to 0. And so if the null hypothesis were true, we would expect any kind of sample difference between sample proportions. We would expect any difference we see be because of random chance, and we would expect those differences to be centered at 0. The central limit theorem says that if your sample sizes are large enough, the difference between sample proportions, that is this quantity, p hat stats minus p hat math, that can be approximated with a normal distribution. The mean of that normal distribution is going to be 0, and then the standard deviation or standard error is going to be this quantity, okay, square root of blah, blah, blah. And, the p hat here is the total proportion of yes. So you add, the total number of yeses divided by your total sample sizes, or the total counts of successes in each sample, and your total sample sizes there. Okay. And when you go through your work and you find to calculate your p-value, the two-sided p-value answers this question. If the true difference in proportions were actually 0, meaning if the null hypothesis were true, how likely is it that two random samples would produce a difference of 0.1 or something more unusual in either direction? So mathematically, that comes out to be, what's the probability that when you take two random samples, the difference between them is going to be greater than or equal to 10 percentage points, 0.1, okay? And I have it in absolute value because it's a two-sided test, so if p-stats is greater than p-math, that's interesting. If p-stats is less than p-math, it's also interesting. We're just looking for an absolute value difference of 10 percentage points or more. And so the calculations end up like so. You take the overall proportion of international students. You do 75 plus 64 is the total number of international students divided by 310 total number of students we surveyed. So we get something like 0.4484. We plug that in into our to get our z score. We get 0.1 divided by 0.0565. We get a test statistic of around 1.77. And now we want to know what is the probability of being at 1.77 or somewhere more extreme. Okay, so the difference here ends up being the area to the right of positive 1.77 or 1.769 and the area to the left of negative 1.769 is going to be 2 times 0.0384. So we get a p-value of around 0.0768. 0.0768. Okay, and if we're approximating with the normal distribution, this is kind of what our diagram looks like. We got a difference of 0.1. We want to know what's the probability of getting 0.1 or something more extreme. So 0.1 and higher, and negative 0.1 and more negative. And when you calculate that, you get about a little less than 4% each tail. Total p-value a little under 8%. So our p-value is around 7.68%. And if our significance level is 5%, then my p-value is greater than my significance level, and I would not reject the null hypothesis. And so my conclusion would be something along the lines of the data we have does not provide evidence that the proportion of international students is different for statistics majors and math majors. And so although we observed a difference of 10 percentage points between our two samples, our sample proportions, that is not that difference is not sufficiently unlikely. Okay, it's not that weird. Okay, under the assumption that the true difference is 0, for us to conclude that there really is a difference in the populations. Okay, so a p-value of around 0.0768 means that this kind of difference, there is a 7.68% chance of seeing a difference of 10 percentage points or larger in random samples of these sizes, if the true proportions were the same. So at the end of it all, we say we cannot say that the observed difference of 10 percentage points was caused by a real difference in the population proportions. It is entirely plausible that it was the result of just chance variation, that there's actually no difference in the populations, and just by kind of randomness, you get a 10 percentage point difference between your two proportions. Okay. Now, to use the z-test, there are certain conditions that have to kind of be true, and basically you need to have big enough samples. Okay, each sample should be large enough that you have at least 10 successes and 10 failures in each group. Okay, so, and the samples have to be independent. And so, as far as our example goes, we have enough. Our samples were big enough, right? We had 150 people in the stats major, so we had 75 international, 75 yes, and 75 no. Okay, for the math major, we had 160, which was 64 yes and 96 no. So in both, all of those numbers, all four of those are bigger than 10. So, a z-test is okay here. Okay, but what do you do if that condition is not met? Okay, if these conditions fail, so if the sample sizes are small, or you end up with proportions that are like close to 0 or 1, then using the normal distribution as an approximation might not do a good job of approximating the distribution. And so in that case, your p-values could end up being inaccurate, right? Could be wrong. So what we can do instead is do a randomization test, and that's what we're going to take a look at. Okay, randomization tests don't rely on the normal approximation, and they're going to be, accurate for smaller sample sizes. For big populations, the randomization test is also going to be accurate. Okay, so we'll look at randomization tests as a non-parametric alternative They don't require the large sample assumptions that the Z proportion requires, and we'll try to build a distribution for the difference in proportions by simulating random reassignment of the data. Okay, so that's what we're going to take a look at. Let me give you your first view quiz answer, which is the letter D. D as in dog. D as in dog is your first view quiz answer. Okay, so for our randomization test, to introduce it, I'm going to play a little video clip. This is from an old TV show called Mythbusters. I don't know if you ever watched this show, but they ran these little experiments and to try to like test out these claims and stuff, and not very scientific, but certainly entertaining. Okay, now the question that they're trying to answer is yawning contagious? Okay, now I have to pause my video recording because it's a copyrighted video. I had to actually like purchase this episode, and so anyway, if I record it, then you get like copyright strikes and stuff. So anyway, I'm going to pause the recording, and I'll just describe it for those of you who weren't here in person. Okay, so the recap, if you didn't watch the video, is that Mythbusters, they wanted to explore whether yawning is contagious. So they conducted an experiment, and they got 50 participants at a local flea market, and each participant was told to sit alone in a small room, and they were monitored for a few minutes. Before entering the room, some participants observed a person yawning, and if they saw that person yawning, we said they were in the seed yawn group. Okay, and then others didn't see anybody yawn before, and they are in the control group. And then the Mythbusters, they watched them and recorded which ones ended up yawning and which ones did not. And the goal is to see whether a seed yawn makes a person more likely to yawn. Okay, so the data, all right, we had a total of kind of 50 people, and I think it's okay to say that random assignment was used for deciding who was going to be in the control group versus who was in the treatment group. Okay, so I think it's safe to assume that the order of participants was random, and every third person was assigned to the control group, and the others were in the seed group. Okay, so this is, generally like random assignment. Okay, it's not like they flipped a coin or something before they went in, but I think it's safe to assume that the order of participants was random. Okay, now also we should keep in mind that this is not a random selection from the general population, so it might be a little tough to generalize to the broader population, but anyway. These were the results. So in the video, they just gave kind of percentages, but you can kind of backwards solve from the fact that they said there were 50 people, and 2/3 of them, were in the control group, or were in the treatment group, and 1/3 would be in the seed group. So as far as the seed group, 34 participants yawned. 34 participants were assigned to the seed yawn group, and of them 10 yawned, and so our observed proportion for the seed group is 0.294, 10 out of 34. And for the control group, there would have been 16 participants, and of them, 4 of them yawned. Okay, and so our p-hat for the control group is going to be 4 out of 16, or 25%. And the observed difference between the two proportions, of 29.4% versus 25%, that's a difference of around 4.4 percentage points. Okay, and they said, the difference isn't dramatic, but given how large our group was, they feel it's confirmed, and the narrator says there's little doubt it does seem to be contagious, that yawning is contagious. That was their conclusion. We're going to run a randomization test and do kind of a hypothesis test to kind of see what we get. Okay, so to put this in statistical terms, we're going to say there are two kind of population proportions or probabilities, and one will be what is the probability of someone yawning if they see the seed yawn, okay, versus what's the probability of somebody yawning if they do not see a seed yawn? Okay, that's going to be the control group. And the null hypothesis is that there's no difference, okay? That yawning is not contagious, so the probability of yawning is going to be the same for both groups. We're going to do P seed minus P control. That difference would be equal to 0 if the null hypothesis were true, that there's no difference between our two probabilities. The alternative hypothesis is that yawning is contagious, so that if you do see the seed yawn, if you're in the seed yawn group, your probability of yawning is greater than if you were in the control group. And we would expect to see a positive difference between P seed minus P control. Okay? That would be the alternative. I should see if people are more likely to yawn if I talk about yawning here. But okay, so our this is what we got in our observed data. Our seed yawn group, we got 29.4%, 10 out of 34. Our control group, 4 out of 16, 25%. We have a difference of 0.044. The question is this difference of 4.4 percentage points, is that large enough to conclude that yawning is contagious, or could this difference be just the result of random assignment? That's what we want to know. Could we have gotten this result just from random assignment? So our null hypothesis, okay, is that yawning is not contagious, okay? And so if that null hypothesis were true, okay, then we have people that would just either yawn or would not yawn, regardless of which group they were placed in. Okay, so we can kind of think of, out of the 50 people, if the null hypothesis were true, then these 14 people who yawned, it was their destiny to yawn. They were going to yawn no matter what. Whether they were in the control or the treatment group, it didn't matter. These people were just going to yawn anyway, okay? So out of the 50 participants, 14 people in total yawn. We happened to get 10 in the seed group and 4 in the control group, okay? But if that null hypothesis were true, those 14 people who yawned, they were going to yawn anyway, independent of whether they were in the seed or the control group, okay? And the only reason why we ended up with 10 yawners in the seed group and 4 in the control group, rather than some other split of the 14, like 7 and 7 or 8 and 6 or whatever, is just the randomness of how the participants were assigned to the group. Like if we did it another day with these same 50 people and 14 of them were going to yawn and they just stood in line in a different order, then we would have gotten a different kind of random assignment, right? So we're saying if the null hypothesis were true, then random assignment alone could lead to a difference in the observed proportions of 0.044 or more just by chance. And the question is whether that difference is likely or unlikely to happen if the null hypothesis were true, if the true probability of yawning is the same for seed and control groups. Okay, so what we're going to do is we're going to try to calculate the p-value, okay, and the p-value is going to be the probability that, assuming the null hypothesis is true, of obtaining a difference at least as large as 0.044 purely by random assignment. And so in our case, we're going to say, what's the probability that when you take 2 random samples and you calculate this proportion in the seed group and you subtract the proportion of the control group, you're going to get a difference of 0.044 or something greater, okay, given under the assumption that in the populations those proportions are equal, okay? And here we're just checking one side because we're assuming our alternative is that yawning is contagious, meaning that the probability of yawning in the seed group is going to be greater than the control group. Okay. Now, when we arrive at our p-value after doing our work, if that resulting p-value is small, less than 5%, we would say that the observed difference we got would be considered a rare outcome if the null hypothesis were true, okay? And so the fact that we got this thing would provide evidence that yawning might be contagious, okay? On the other hand, if the p-value is not small, okay, some big number, then that would suggest that the difference we observed of 0.044 could have just easily happened by random assignment alone, okay? Even if yawning is not truly contagious, right? So this is how we're going to interpret our p-value at the end. Now, keep in mind, the participants themselves were not a random sample from a broad population, so any formal inference is strictly about these 50 individuals, okay, or individuals in similar conditions. And trying to generalize to all people is, a little bit shakier without a proper randomized sample from the population at large. But again, that's kind of tough to pull off. But yeah, one could argue that because they went to the flea market early in the morning, we're going to get people who are less likely to be yawning in the first place or something, okay? So, perhaps if they wanted to get a more representative sample, they would need a different way of selecting people, but, it was a convenient sample is what you end up having, okay? But we did use random assignment as far as who is in the treatment group and who's in the control group. Okay, so here we would want to use the randomization test because using the z-test, our sample sizes are pretty small. We had 34 in the seed group, 16 in the control group. Rather than relying on z-test where using the normal approximation is questionable, we could use a randomization test. The randomization test doesn't make any assumptions about the sampling distribution, and instead we are going to simulate what differences are possible under the null hypothesis that there's no effect, okay? And so the big idea behind a randomization test is to simulate what the sampling distribution of outcomes could be when the null hypothesis is true, okay? The null hypothesis says that the random assignment of treatments is a source of variation between the sample proportions. And so what we're going to do is we're going to take data where 14 people are destined to yawn, and we're going to just split them into two groups. 34 people will go into group A, and 16 people will be into group B, because that's what we had for our treatment and controls groups. Treatment, there were 34 people in the treatment group, 16 in the control group. So we're going to make two groups of 34 and 16, a group A and a group B. But we know that who ends up in group A and who ends up in group B is just a result of kind of our random process. And we're going to calculate the proportion of, quote, yawners in each group and find the difference between the group proportions. And here, because we did the random assignment ourselves, we know that who ends up yawning in each group, the difference between the group proportions is just a result of the random assignment process. So this is going to give us an idea of what kind of values we could get from randomization if the null hypothesis were true. Okay, so just to kind of recap what we're doing, under the null hypothesis, a person's likelihood of yawning doesn't depend on which group they're in. In our study, 14 out of the 50 people yawned in total. Okay, if that null hypothesis is true, those 14 people are just destined to yawn, whichever group they end up in. And what we're going to do is we're going to just reshuffle basically those 14 out of the 50 participants, and we're going to just kind of mix them up into two groups. Each shuffle represents another possible way random assignment could have happened if there really was no difference between the groups, right? We're just trying to see what could happen if the null hypothesis were true. Okay, and so for each shuffle, we're going to compute the difference in proportions of yawners between our two groups, and this is going to give us a distribution of the possible differences that could be if the null hypothesis were true, under the null hypothesis. And we're going to compare our actual observed difference of 0.044 to our simulated null distribution to decide if it is unusual or not. So what enables us to do this, the reason why this is safe for us to do, I guess, mathematically, is that we have exchangeability in our outcomes, okay? If exchangeability doesn't apply, you can't do a randomization test. Exchangeability is the idea that if the null hypothesis were true, all possible permutations of the data are equally likely, okay? And it also means that any permutation of the data is exchangeable with any other permutation of the data, again, if the null hypothesis were true. So on at a practical level, this means that exchangeability applies when you have experiments where random assignment has been used. If there was no random assignment in the gathering of the data, don't use the randomization tests. Okay? If the patients are assigned treatments randomly, then any assignment arrangement of patients is equally likely. Okay? If Mythbusters visited the flea market, like in a parallel universe, and they still have the same 50 people, but they just stood in line in a different order, who ended up in the control group and who ended up in the treatment group would be different, right? And any kind of random shuffling of the people, is equally likely. It doesn't kind of mess up the way the experiment was run. And if the null hypothesis were true, then any of those arrangements are just as valid, okay? But in cases where treatments were not assigned randomly, like if you do an observational study and you don't do any kind of random assignment of treatments, then the permutations of groups are not equally likely, and you should not use a randomization test. Okay, but here we're going forward with it, and so this is how we're going to set up our data. I'm going to create a vector called yawning, and this is going to have true and false values. True is going to represent people who yawned, false for people who did not yawn. We had a total of 50 people, and 14 of them yawned, and I'm going to set my first 34 to be kind of my treatment group. So here I'm going to say I've got 10 trues and 24 false for the first 34. And then the remaining 16, I have 4 true and 12 false. And that gives me a total of 14 true values and 36 false values. Okay. And so in the treatment group, I have 10 out of 34. And if I call mean on this, because it's true false, it's going to give me the proportion true. I'm going to get 29.4%. And if I call mean on the control group, which has the remaining 16, I get 25%. And so my observed difference between proportions is going to be 0.294 minus 0.25. I get a difference of 0.044. That's my observed difference. We're going to keep that. Okay. And what we're going to do to conduct our randomization test is we are going to shuffle our yawning vector. So I can call sample on yawning, and if you call sample on an existing vector, what it does is it takes the vector and it just shuffles or permutes the values. Okay, it's going to keep all 50 values the same. So there's 14 true and 36 false. The shuffled vector will still have 14 true and 36 false if you just call sample on yawning. Later on, we can add extra arguments like replace equals true, and then you're sampling with replacement. We're not doing that. Here we're just shuffling them. Okay, we're just doing a permutation that's going to be sample. All right, so here is just one randomization trial. I take my vector of 50 true false values in yawning, I sample them, and that's going to give me randomized. And I'm going to just take the first 34 values and put them into group A. So this is going to be just 34 shuffled values. I take the remaining 16 and I put them into group B. That's going to be just 16 shuffled values. I calculate the proportion in group A and the proportion in group B, and I take the difference between them. And when I do this, I get a difference of 0.044. So this was just one possible difference purely from random assignment. Here I can see there's no reason why I should end up with more or fewer true false values in group A than group B or whatever. This is just a randomized result. Okay, the difference we got is 0.044, and that's equal to our observed difference that we got in our original data. So this suggests that the observed result that we got in our original data could just be random noise. Okay, could be. Now, what we're going to do is we're going to repeat this to see how often stuff like this happens. And if it's often far below 0.044 or above that, okay, then 0.044 might be unusual under the null, but we'll just kind of see. Just here's another randomized trial. Here I shuffle yawning again, put some in the randomized group A and some into group B. Again, who ends up where is just a pure result of randomness. And when I calculate the proportion there, I get a difference of negative 0.139, okay, negative 0.14. And it turns out, in group A, the proportion was around 23.5%, and in group B, the proportion was around 37.5%. So that's a difference of around negative 14 percentage points, okay? And, when you do this, sometimes group A is going to end up with a higher proportion of true than group B. Sometimes it's the opposite, okay? And, that variation that we see is really just from randomly rearranging my yawning vector of true-false values, okay? There's no other source of variation here. It's just the randomizing process. And we really want to just see what kind of values we can get from the randomizing process. So here I'm going to just say, let's do this a bunch of times. And I tell the computer, do this 10,000 times. Okay? So I'm going to create a vector to store all of my differences. I'm going to do this 10,000 times. And I do a for loop for I and sequence along differences. So this is going to be 1 through 10,000. What do? We take that vector of true, false values and I shuffle them. I'm going to just put 34 into group A, 16 into group B. So whoever ends up in group A and whoever ends up in group B, that's just a result of the shuffling process. I calculate the proportion of group A and the proportion of group B, and I take the difference between them and I store them in a vector, and difference is square bracket I. And after doing this 10,000 times, this is the result. Okay, this is the result. The summary, sometimes I get differences as negative 0.599. Sometimes I get differences as great as positive 0.411. My median difference is 0.044. The mean of all of these differences is right around 0.00198, okay? Sometimes negative 0.047, sometimes as high as 0.136. We can take a look at trying to get a p-value, okay? So our observed difference is 0.044, 11765, all right? Our alternative hypothesis is one-sided. We're expecting the seed group proportion to be greater than our control group. So our p-value is going to be the proportion of simulated differences that are at least as large as 0.044 or something greater. So I'm going to say, are my differences greater than 0.044? This is going to give me a true-false value, vector of 10,000 of these things, and the mean is going to give me the proportion of that. And it says you get a proportion of around 50%, 51% of your values are true, okay? So this is the diagram, okay? It is a discrete distribution because I have a total of 14 people who yawned, and so there's only a certain number of ways I could split those between two groups. One way is I can get 10 in one group and 4 in the other. I could get 11 and 3, 12 and 2, okay? Or in the other way, I could get 9 and 5, 8 and 6, 7 and 7. Okay, there's only a limited number of ways to split it. So this one is kind of 10 out of 34 versus 4 out of 16. This one would be, I think, 9 out of 34 and 5 out of 16. This would be 8 out of 34 and 6 out of 16. And I think this one over here is 11 out of 34 versus 3 out of 16 and 12 out of 34 and 2 out of 16 or something like that. So there's only kind of a limited number of things. And we can see, we got a difference of 0.044. And, in this distribution, it's not that unusual. Okay, there's quite a few at 0.044, and there's still quite a few at that number or even greater. Okay, and so my p-value is, 50%, 51%. And so this suggests that seeing a difference of at least of 0.044, there's a 51% chance of seeing a difference of 0.044 or more if the null hypothesis were true. So that's a big number. That's not small enough. Our significance level is 5% to reject the null. And so what we're going to conclude is the data do not provide convincing evidence that a seed yawn makes people more likely to yawn. Observing a difference of 0.044 seems quite likely to occur just by chance if 14 out of 50 people are going to yawn regardless of treatment. Okay, So we cannot say conclusively also that yawning is not contagious. It's just that our data simply does not provide evidence that it is contagious, okay? It is possible that a seed yawn actually does increase the probability of yawn, but maybe we didn't collect enough data, or maybe what we observed is just a weird kind of result that leads us to believe that it's not. It's also possible that randomized worked against us too, okay? We could try a two-sided alternative if we were curious to see if seeing a seed yawn has any effect, positive or negative. Our alternative would be, P seed minus P control isn't equal to 0. So this would be kind of like, if you see someone yawning, then you're like hyper conscious about yawning, and so you try to make sure you're not going to yawn yourself or something like that. I don't know. Okay, so we'd be interested in seeing either a positive difference that it makes you more likely to yawn. Also interesting if you get a negative difference and it makes you less likely to yawn. So in this case, we're going to use absolute values and would say, okay, the absolute values of our differences has to be greater than or equal to the absolute value of our observed difference. Okay, and when you do that, we get 1. Okay, we get a p-value of 1, meaning every single randomized shuffle has an absolute difference of at least 0.044. Okay, and that happens because, again, as far as the different splits that are possible, it's you either have like a 10-4 split. Notes. Okay, so you could have a 10-4 split, 4 out of 16, and you take the difference. Okay, right. So this is what we got, 0.044. But the other possible differences are like 9 and 5. A 9-5 split results in a negative value. And so that's even larger, like the absolute value is greater, 0.0477. And then anything like further in that direction, like an 8-6 split or a 11-3 split. So this is going to give me an even more negative number. Okay, even more negative, and then the other being kind of 11 and 3. Okay, you get something more positive. So if you're looking at what are the possible differences, you can get 10-4, 9-5, 8-6, 11-3, and anything else, everything just results. It is not possible. There's no arrangement that gives you anything smaller than 0.044. Okay, this is quite literally the smallest or the least extreme value in the null distribution. Okay, so again, looking at this is the 10-4 split. This would be the 11-3. This would be a 12-2, 13-1, and 14-0. And then this would be 9 and 5, 8 and 6, 7 and 7, 6 and 8, 5 and 9, so on and so forth. Okay, and this is 0.044, and this one's negative 0.047. It is impossible to get anything smaller than this, anything closer to 0. So, so our result is that the observed difference that Mythbusters got is not impressive at all. They said it's not a big difference. Yeah, it is literally impossible to get anything smaller than a 4.4 percentage point difference. Okay, so it's not large. So yeah, we would not really provide any evidence that yawning is contagious. Okay, just a few additional things here. So. Oh, how many view quiz answers have I given you? Just 1 so far? All right, let me just go ahead and give you your last 2. E as in elephant is your second one, and C as in cat is your third answer. So E and C. E and C. Okay, so again, the randomization test assumes each participant was equally likely to be placed in either group, that the data came from proper random assignment, And in our Mythbusters example, it's nearly random assignment. We just said every third person is assigned to a control group. And again, I think it's safe to assume that the order in which they kind of stood in line is fairly random. So I think the randomization assumptions there are reasonable. Okay. Our large p-value means our observed difference is not unusual if yawning is unaffected by seed yawns. And so our data do not provide strong statistical evidence for the idea of it being contagious. Okay. Now, insufficient evidence does not mean disproof. Failing to reject the null doesn't prove that yawning isn't contagious. All we can say is that given our sample, our small sample, we cannot confidently claim that it is contagious. Okay. Now, it is possible for any finite sample, it is possible to enumerate all possible permutations. Okay. And that would give you an exact p-value, right? So, but for a data set like this, enumerating every single possible arrangement, there's a lot. It would be 50 choose 14, okay? As far as like how many possible ways are there to do this. And so, because that is too big, we just simulate this and we do something like 10,000 permutations to get an approximate distribution. Now, 10,000 is probably more than enough for a pretty stable estimate of our p-value, and you can try it out and just try to do one set of 10,000, another set of 10,000. You should get p-values that are pretty similar in most cases. You could try doing something like 100,000, but your gain in accuracy is probably going to be fairly modest there. Okay. The key principle is that if the treatments were assigned completely at random, then under the null hypothesis, every single rearrangement of who gets which treatment is equally plausible, and that the interpretation at the end is that if the data you observed appear to be kind of extreme relative to the distribution of all of these other equally plausible outcomes, then that's going to provide evidence against the null hypothesis. Okay. If we compare this to, say, the z-test or even a chi-square test from like classical statistics, they're both what they're both trying to do is they're trying to quantify how unusual our observed results are under the null hypothesis. Okay, in the z-test and the chi-square test, they're relying on large sample approximations using a normal distribution or a chi-square distribution to simulate or understand what the distribution of outcomes looks like if the null hypothesis were true. Okay, the randomization test doesn't make these assumptions. It just says, hey, let's try to simulate what the distribution would look like if the null hypothesis is true, and it just assumes kind of the random assignment there. All right, and so the randomization test works well or has advantage in these kind of small sample settings where we have 34 versus 16 or something like that. You often get results that are kind of more accurate than a z-test, just because the normal approximation might not be very precise. The only time where the randomization test will fail, and this is generally going to fail in all cases because you didn't collect enough data, is if you have like a total if you have like 50 out of 50 or 0 out of 50, okay, then there's nothing to randomize at all because everybody's just the same, right? And then also if you only have like 2 yeses total, right, 2 out of 50 yeses, then there's really only like 4 possible results. You can either get like both in group A, one in group A and one in group B, or both in group B. Those are really the only 3 possible results. So like if you only have a couple like yes cases, then you still don't have enough of a sample size. So you need to make sure you get like enough observations so you have at least a decent distribution there. Okay, and then this is just warnings for any kind of hypothesis test, and that is failing to reject doesn't prove the null is true. Okay, and then again in this case here we didn't have random sampling, we just had random assignment. Okay, so trying to generalize to a larger population is a little bit more speculative there. Okay, so we'll end here for today. Have a great rest of your day, and we will see you on Wednesday.